Mr. Wojciech Gora from Harvard University, who's going to be giving a talk on ultra-fast laser machining of porcine sclera.
I really appreciate that German accent at the end. Why do you have to do that?
We have to cover all the angles.
Wojciech.
You're gonna record it as well?
No, I'm gonna measure time. Like 12 minutes. Time's just started.
Fuck off.
Well, you shouldn't say that.
No.
I'm saying it to
I didn't
him.
record that.
To him, and to him.
Well, save it for the comments. Wojciech.
It's distracting.
Wojciech.
Thank you for the introduction. It's great to be here. So, as previously mentioned, I'd like to talk with you about ultra-fast laser machining of porcine sclera. The ultra-fast lasers provide us with the possibility of removing biological tissue without introducing a lot of thermomechanical damage to the ablation site or to the surrounding tissue. It's pretty much due to nonlinear absorption and plasma removal, you can do that, that's pretty bad. How to rephrase that? Well, the tissues that are transparent at low irradiances, a certain wavelength, they can be removed due to nonlinear absorption, which removes plasma. Alright, I'll work on that later. Well, potential benefits of removing the sclera, the thinning the layer, is you can decrease the intraocular pressure and increase permeation through the tissue. So here we can see how the removal mechanism works for plasma-mediated ablation. When the irradiance is high enough, then therefore due to multi-photon absorption, plasma is created. You can pretty much see here below the threshold there will be no plasma, and all the energy will be just deposited into the tissue, to the sample. Then whenever the certain intensity threshold is reached, plasma starts to appear, and plasma has much higher absorption than the tissue itself. Therefore, the absorption depth is much smaller. So we're not putting all of the heat like into the tissue, but just close to the surface, and we're actually gonna remove that. Yeah, it's like when the further into the pulse, where the intensity still goes up, the plasma is gonna grow above the surface rather than beneath it due to pretty high absorption coefficient. So first, few words about our experiment. Like, we used porcine sclera samples for our experiments. We did that due to the samples are highly similar to the human tissue. They have similar collagen organization, similar water content, and similar histology. Samples were prepared with either 5 or 8 millimeters diameter trephines, which would be explained clear later when they need to be circular so they can fit into the equipment. Samples were stored in the PBS solution, so they were kept hydrated before they were actually laser machined. So this is laser we use. This is a Triumph true micro picosecond laser operating at the wavelength of 10-30 nanometers, 6 picosecond pulse duration, repetition rate up to 400 kilohertz. Probably the most important part of this setup is the galvanometer scan head that allows us to test many different scanning patterns, which is quite useful when investigating the behavior of the tissue while in machining. After samples were machined, they were fixed in glutyraldehyde and post-fixed in osmium tetroxide. Consequently, they were critically point-dried using liquid carbon dioxide. After they've been fixed, they have been coated with 20 nanometer layer of gold. So they were prepared to be investigated with the SEM, and consequently to get the depth and the profile of structures created. They were investigated using surface profilometer Alicona. So our first experiment was a single light scanning ablation. We have tested many pulse energies and few different laser repetition rates. As we can see here on the plot, the difference in the depth for different repetition rate is quite significant. This is due to the effect of heat accumulation. Due to low thermal conductivity, the heat from previous pulse is still there whenever the next one comes. That's why for the highest repetition rate that we tested here for 10 kilohertz, there's such a huge difference compared to 100 hertz or even 1 kilohertz. This heat accumulation effect will be much more visible whenever we go to the next experiment, when we're gonna show the whole area removal patterns. So here we tested 4 different patterns. The first one is the stipple raster scan. Second was the snake-like pattern, which is a raster scan with alternating directions. And then both stipple raster scan at an angle and at an angle with alternating directions. So here for the first 100 hertz repetition rate, there's been barely any tissue removed with depth of 30 to 40 microns at the very end of the cavity created. The scanning starts here where the red dots are. So the depth will build up across the scanning pattern due to previously mentioned heat accumulation. Then if you go to the other end of repetition rates for the highest one, the tissue is deformed. It's like the heat accumulation is too much and just deforms the whole tissue, and we have a lot of thermomechanical damage present here. Best results were achieved for 1 kilohertz repetition rate. The cavities were deeper than for 100 hertz repetition rate, but there was still no damage, thermal damage introduced as in the case of 10 kilohertz. Here we have a better view of how does the profile of the cavity looks. We can see that where the pattern starts is the shallowest, and then as we go further, the heat that's accumulated builds up and removes more tissue for every scan. Next scanning patterns that were tested was a circular scanning pattern. We have tested 4 different ones. First two was the concentric circle scanning pattern inbound and outbound, and the spiral inbound and outbound as well. As in previous slide, the red dots show where the scanning pattern starts. In the case of 10 kilohertz repetition rate, similar as for the simple square area removal, the tissue is really deformed. It's probably even more than in the previous experiment. Therefore, this repetition rate is not suitable for removal of biological tissue, because it will just destroy everything. For 100 hertz, it's a similar case as for this square area removal. The cavities are visible, but they're not deeper than 40 to 50 microns. I mean, if that's what someone needs, then it's fine. But best results were achieved for 1 kilohertz, especially for the outbound spiral scanning pattern. So the scanning starts in the center of the tissue, and the heat accumulation effect is spread uniformly during the scanning. The laser beams in contact with the tissue all the time, therefore the heat spreads uniformly in all directions, and the heat accumulation is equal across the ablation site. And therefore, in this case, we are able to create a cavity which has a flat surface. For this particular pattern, we have tested many different pulse energies.